Yeah, so that's live. Hello. This one. Back at it again.
Yeah, hope you've had a pretty good day.
Yeah, I had a midterm this morning. It's kind of bad.
Must have been a lot of work.
It's okay. Don't worry about it. You can enjoy it. You can sit back and enjoy it. Are you Harsha?
Yeah.
Okay.
What's up?
Because I've seen your Discord profile pic.
Yeah.
I was like, yeah. Alright, it's 5:30. Do we want to start now?
Yeah.
We'll wait like one more minute. Yeah, the live stream's on. Hopefully they can hear me too. Does this work? Oh, it's fine. Okay, it's 5:31, so we're gonna start. So, thank you for everyone coming out. No, it's midterms. I had a midterm this morning. It was 3341 for CS. I probably failed, but it's okay. Here to teach you guys about deep learning. So today's gonna be part 2. So last week or 2 weeks ago, we talked about manipulating data with pandas and NumPy. If you weren't there, the GitHub repo I'm about to give you has all the stuff in there. Slides, workshops, exercises and stuff like that if you want to go over it. This is completely different from what we did before. This is going to be more theoretical. There's going to be a lot of linear algebra, calculus, so it's okay if you don't get all of it, especially if you're a freshman or stuff like that. Just be sure to take a look afterwards, and I'll be sure to put supplemental resources on the GitHub when I get home. So, who am I? Huh? Oopsies. Okay, now it should be good. Yes.
Wait.
If you guys want to join this link, this is how I get questions. So if you want to ask a question, go to that link and it will come up on my screen and I'll be able to answer it. Anyway, let me go next. So who am I? My name is Aaron. I've done most of the workshops so far, if not all. I'm the project director, so I help coordinate all the workshops. There's gonna be a bunch more by my project coordinators, which are coming soon, which are super interesting, and they're delving into different subfields of artificial intelligence, deep learning, and such. So there's my email too, if you want to reach out for anything, questions about anything, I'll reply. And if you want to reach out about any questions about this workshop afterwards, if you have an idea, or I'm on Discord too. I have the director's role, so if you want to message me there, that's fine. So everyone go to this link. It brings you to GitHub repo. There's the slides. It's called Introduction to Deep Learning 2. There's also Introduction to Deep Learning. Make sure you don't click that one. That was a 2-week-old workshop. We also have some notebooks in there. If you look, those are from 2 weeks ago, and those are just basic exercises. After this, I'm going to be adding exercises pertaining to the theory side of things and a little contest beginner notebook that we'll talk about at the end of this workshop. So I'll just give everyone a couple more seconds to just access that and make sure you can open the slides and stuff like that. It's a PDF file. If you don't know how to use GitHub, just raise your hand or you can ask on here. We help you because GitHub is definitely confusing, especially the first time I use it. So intro.nasano.me, if you go to the link, it's in there. Don't forget you can ask questions through there. So let's get started. So this is the agenda we're going to be going over. So it's going to be perceptrons, activation functions, loss, how to optimize for loss, gradient descent, back propagation, which I was going to talk about, and we might not get into it. mini batches, which has to do with gradient descent, but optimize, and then dealing with overfitting. If you don't know what these words are, we're going to be going over them. You'll definitely learn about it a bit. So let's start with the fundamental building block of deep learning and of every neural network, which is a neuron, and it's also known as a perceptron. You've probably heard of it. So we're going to walk through what a perceptron is, how it's defined, and we're going to build our way up so that we can build a whole entire neural network by the end of this workshop. So the idea of a perceptron, or a single neuron, is actually very simple. So it's really important for all of you to understand this at its core. So let's start by actually talking about forward propagation of information through this single neuron. So we define a set of inputs, x1 through xm, which you can see on the left-hand side. And each of these inputs, or each of these numbers, are multiplied by their corresponding weights and then added together. So we take the single number, the result of that addition, and then we pass through it what's called a nonlinear activation function to produce our final output y. So if you look at the formula on the right, we have y hat is equal to g of something, which is g is the nonlinear activation function, which we'll be talking about later. And we can see that there's a sigma sign summation from I equals 1 to m of xi wi. So that's just multiplying the inputs times the weights and then summing them all together and putting them into the activation function. So the right side is just the mathematical representation of the left. So technically, that's not entirely correct. There's a little bit more, and that's what we have to add. It's called a bias term. And this is basically like the y-intercept of y equals mx plus b. It lets you shift around the activation function left or right to correspond to fit your data. So now on the right side of the diagram, you can actually see this concept illustrated or written out mathematically as a single solution. And you can actually rewrite this in terms of linear algebra in matrix multiplications and dot products to represent this a bit more concisely in the next slide. But I just want everyone to understand this, that the left diagram is directly represented on the right. It's a mirror. It's just a way to visualize the right equation. So just go through it, make sure you get this. And it's a really core concept. And the basis of all neural networks is just this, the perceptron. So let's convert it to linear algebra so that we can make it more concise and more easier to read and more in terms of what we do with the equation. So we have capital X, which is a vector of our inputs, x1 through xm. And then we have W, which is a vector of our weights, w1 through wm, which you can see on the left diagram. And these are vectors of length m because they go from 1 to m. And then their output is very simply attained by just taking the dot product by transposing x, multiplying it by w. Basically what that does is it does x times w for each row, if you don't know what transposing is, and I mean dot product. And then we add the bias, which in this case is w0, and then we add on nonlinearity through the function g. So if we just take a look at this, we're just converting the gray equation up top to linear algebra. They do exactly the same thing. It's just that we're working with matrices rather than individual terms within a summation. So why is the activation function nonlinear? Good thing you said that, because we're going to talk about it right now. So I've been mentioning nonlinearity in the form of g. So g is not a number that you're multiplying in. It's actually a function. You're inputting w0 plus x transpose dot product by w into a function. So if we take a nonlinear function, what is that? It's a function that's not linear. So that means it's anything besides a straight line. So for example, a really popular activation function that's nonlinear is called the sigmoid function, which you can see graphed there, and you can see it there in its mathematical form. There's actually a lot more activation functions out there. We're going to talk about 3, which sigmoid is one of them. We have sigmoid, a hyperbolic tangent, and then we have rectified linear unit, also called ReLU. So we're gonna, if you see on the bottom, there's some code snippets. These are basically just TensorFlow Codebox, which illustrates how we can take some of these topics mathematically and convert it practically using TensorFlow, which is a machine learning library that if you ever do decide to go further into machine learning or deep learning, it will be used a lot throughout as a general library that you use. So we can see that sigmoid is represented by math.sigmoid, hyperbolic tangent is represented by math.temh, and then we can see that ReLU is used from the NN library, short for neural networks, because ReLU is used throughout neural networks. And the reason why is because, as we can see, ReLU is actually a piecewise function. Before 0, anything before 0, so any negative number, equates to 0, but anything past 0 equates to 1. And what this does is it allows us to simplify simplify calculations. So whenever we do billions and billions of calculations for billions and billions of neurons, we don't have to simulate a curve or a tangent curve and stuff like that. We can just have a very easy piecewise function to go by. So the reason why we use activation functions is that it's a function that gives output and takes output of any real number and any activation value, and it always outputs a number between 0 and 1. So why is this important? This is important because a lot of machine learning and neural networks in general, and deep learning, has to do with probability. So if you know from stats, probability is from 0 to 100%, but in reality it's represented by 0 to 1, where 1 is 100% and 0 is 0%. So just understand that we use this to help convert numbers into a probabilistic output. So one really important question that I hope you're asking yourself is, why do we even need them? And so I want to say that no matter what in this workshop I hope you're always questioning, because questioning is the way you learn. So always question why we're doing things, because we don't just do things for just because I said so. There's a reason behind everything, so make sure you try to figure out that reason. So why do we need activation functions? The point of an activation function is to introduce non-linearity, like I talked about before, into our networks, because these are all non-linear functions, as you can see. ReLU was non-linear. Hyperbolic tangent was like a low curve, and the sigmoid was also a curve, which are not linear. So it allows us to deal with non-linear data. As we know, in real life, most data is not linear. So imagine if I told you to separate the green points from the red points, but all you could use was a single straight line, right? You might think it's easy with multiple lines or curved lines, but you can only use one single straight line. And that's what happens when you use a neural network that doesn't have a nonlinear activation function. You'd only be able to split it into two halves. Basically the best fit line, just a single line. And obviously this wouldn't best fit the data. It wouldn't fully represent the data. So that makes the problem really hard when you don't use nonlinear activation functions, because no matter how deep the neural network or how many neurons you add, you'll only be able to produce a single line decision boundary, and you're only able to separate your sample space with only a single line. So whenever we use nonlinear activation functions, this allows your neural network to approximate arbitrarily complex functions, and that's what makes neural networks extremely powerful. Instead of just drawing a single line, we're able to curve that line around to best fit the data, and it lets us to cluster the green and red like it's shown on the right rather than the left. So let's understand this example. Let's understand this with a simple example so that we can build up our intuition. So imagine if I gave you a trained neural network. So a trained neural network means the weights are already established. And we can see the weights on the left side. It's 3 and -2, and then we also have a bias of 1. So this network only takes two inputs, x1 and x2. And if we want to get the output of it, we just have to do the same thing as I said before. So first, we have to take the dot product of our inputs with our weights, and then we have to add the bias and then apply it to a nonlinear activation function, which you can see is done on the third line. We can see that it's 1 plus the x transpose dot w, and then we can see that the output is just a two-dimensional line which represents a weighted combination of our inputs. So 1 plus 3x2 minus, it should be 3x1, that's my bad, minus 2x2. This is basically a line that we can plot. So why do we want to plot it? Basically, when we plot it, we're able to create something called the feature space, or also known as the input space. That's what that graph is. So we can see that the x-axis is x1, which is a feature that we input, and then x2 is another feature that we input. So this line corresponds to all the decisions that your neural network can make, because let's say, for example, I give you a new data point. If we want to predict -1 and 2, those are the inputs. We could see where it lies in the decision boundary, and we're able to predict what the neural network would be put out. This is really basic, as you can see. It only has 2 features. Over time, we're able to add more features, and that would add extra dimensions. So we go to 3 dimensions, 4 dimensions, so and so on. And we would be able to have to form a complex line that interweaves between all these dimensions that we have to train our model on, that fully divides the input space so that we can accurately predict an output from an input. So if we take -1 and 2, we can plug it in the bottom left. We can see that y equals g of 1 plus 3 times -1 minus 2 times 2. And then we plug it into the activation function. In this case, I'm using the sigmoid activation function, and we get 0.002, which would be the output of our neural network. So everything is able to be calculated by hand, especially at this small scale. This is the basis of neural networks. We have weights, we have inputs, and we have outputs, and then we also have biases. You see any slides? There is a sign-up sheet for this meeting. It will be later on. So now if we remember, the sigmoid function divided in the space into 2 parts. And so if we see that anything less or to the left of the boundary is classified as such, and anything to the right of the boundary is classified as such. And so this basically just lets us visualize the input space that we're generating using the neural network. So now that we have the basis with a neuron or a perceptron, we're able to build complex neural networks with perceptrons. So let's see how they all come together. So let's revisit that diagram of the perceptron I've shown you before. If there's only a few things they differ in the workshop, I really want everyone to take away how this works, because this is the core basis of all neural networks and deep learning. And so there's 3 steps. Don't forget these. I want you guys to remember all of this. So the first thing is that you dot product your input and your weights. Basically, you're multiplying the corresponding node with the corresponding weights. That's all it means. And then you add a bias, and then you apply your nonlinear function. Those are the 3 steps. That's it. You multiply the corresponding weights and inputs, and then you add them together. You add a bias, and then you apply a nonlinear function on it. That's it. That's the basis of all deep learning, stuff like NLP and things like that. Any machine learning model that you probably can think of, deep learning model specifically. So let's simplify a bit, and let's remove the bias just for simplification purposes, so that we don't really have to think about it that much, and it just makes everything more complex theoretically. So if we can look here, we simplified it. What did we do? We took out the bias, and then we moved the activation function to a line instead of putting it as its separate node. So we can see that Z is the result of the dot product plus bias before we apply the activation function. And then we can see that the final output is Y, which is equal to the activation function of Z, which is called our activation value. What does the output of the neural network tell us? For example, where the output was 0.002. What does that mean? So in that case, it was just a non-arbitrary number. I mean, it was just an arbitrary number. It didn't mean anything. But as you can see later on, it can be things like we put in the number of hours that you studied for class and the number of lectures you attended. And then you'll be able to output the probability of whether you would, of how likely you're able to pass the class, or what your final grade was, or whether you'll pass the class at all. And that can be applied to many things. It can be applied using various housing statistics. You can predict housing prices using distance from schools, property taxes paid in the region, average income around the region. All these numbers you're feeding in, it lets you be able to predict an output, which can be anything you want pertaining to the data. So it can be for image classification. You can be given an image. Each pixel would be a separate input. And on the output, you would label it, whether it was like a dog, a cat, an orange, or an apple, and so on and so forth. So the output is basically what you want to be predicted. Okay, so now if we wanted to define a multi-output neural network, we can actually just simply add another perceptron to the picture. Instead of having 1 perceptron, we now have 2, which means we also have 2 outputs. So each one is a normal perceptron. There's nothing different. It's like everything we talked before. And we can see that it's taking input from each of the x's, 1 through xm. So what we do, if you look at the formula, it's the same way. We just add an I. I is corresponding to the output neuron, perceptron that is corresponding to, but each one is calculated differently. So we have 2 outputs instead of 1. So you have to do the formula 2 times. So this is also called dense layers. The reason why it's called dense layers, also called fully connected, is because each one of the neurons of the input is connected to each of the output neurons. This makes it a fully connected layer or a dense layer. if you'll see that a lot, that's just basically what it means. So let's try to see how we can actually build up a dense layer like this all the way from scratch using TensorFlow. So we saw the math earlier, but now let's put it into practice. So we can see that we initialize a dense layer, and we're creating an object. And we can see that we initialize the weights and biases. We can add a weight and then add a bias. And then we can see that we can see the input dimension, output dimension. And then we have a call, so that when it's called, we're able to forward propagate the inputs. Basically what that means is the formula that we were talking about earlier. So we calculate Z, which is, don't forget, the dot product of W and the inputs, X, plus the bias, that's what outputs in Z. And then output is tf.math.sigmoid. Sigmoid is our activation function, and we're applying our Z into the activation function, which gives us our output, also known as the activation value. So all that math that we've seen before in the diagrams, this is how you would represent it in Python in actual code. And it's kind of hard to first understand, and especially if you don't know Python syntax. I know some of you have not fiddled with Python before, it's kind of hard to understand. So I recommend coming and look back at this so you can fully understand what's going on. This corresponds to the mathematical equation from earlier, so I just try to figure out, I would try to figure out how to correspond that one for one. So if we wanted to do in TensorFlow, not from scratch, this is actually how we do it. Layer equals tf.layers.layers.dense. Don't forget, dense layer means that it's all the inputs are connected to each output thing. And we can see units equals 2. The number that you put there is the number of output neurons. So we can see units equals 2. That means there's 2 outputs. So let's take a look at what is called a single layered neural network. So this one is, we have a single hidden layer between our inputs and outputs. And that layer is called the hidden layer because unlike an input and an output layer, the states of the hidden layer are typically unobserved and they're hidden to some extent, therefore the name. So since we have this transformation, so from the input layer to the hidden layer, and then from the hidden layer to the output layer, each of these layers are going to have their own weight matrices. So instead of just having input-output, which would just have one set of weights, now we have 2 sets of weights, so we have to figure out how to deal with that. So if we can see that Z is calculated like we did before. It's just summing the weights times the inputs, or in this case would be just X. And then we're adding it to the bias, and then it goes over. And then if we look at the final output, we're basically applying the activation function. So if you see, we're not applying the activation function to the inputs to the hidden layer, but we are from the hidden layer to the output layer. This is very complex. I wouldn't feel bad if you don't get it, but just take a look at this and just look at all the math and try to correspond it to the diagrams. That's basically what I can say. It's a really big conceptual thing you have to get over. And you just have to understand that it's just the summation is multiplying the weights and the inputs, and then you add the biases, and then it just all connects together through addition. So let's simplify it a bit. So if we're going to do 1 neuron in the hidden layer, we can see, let's take Z2. So because it's fully connected, it has X1, X2, and XM connected. So we can see that we have W02, which is the bias. And then we also have the summation of Xj and Wj2. What does that mean? That's the summation of all the connected inputs being multiplied together and then added. And then we can see that the full formula is on the bottom, fully expanded. So this is just 1 neuron from the hidden layer. This is done for each neuron in the hidden layer. And then it's done again for each output. So as you can see, that neural networks are basically a lot of repeated math. It's the same formula calculating for each neuron. So the more you add, the more math you do, but a lot of it is repeated. And this is how you do it in TensorFlow. So the X just means it's fully connected. I'm going to use that to denote fully connected from now on. And so we can see how we can create this exact neural network in TensorFlow. If you can see that we're creating a sequential model, which that means it's a hierarchical model, which means it's sequential and that the layers come one after the other. We can see that we have a dense layer with N. If we can see the input layer is there, the layers.dense N is the hidden layer because the hidden layer is from Z1 to Zn. So we're creating a layer with N number of layers, that's hidden layer. And then as we can see, there's 2 outputs. So to create a dense layer with 2 neurons. And then this is how you represent it in TensorFlow. So it's really easy. And it does all the math for you. You just have to understand the core basics so that you actually know what you're doing and you don't just randomly type things down like a monkey. So if we want to create a deep neural network, all we have to do is just keep stacking these layers to create more and more hierarchical models. So if we can see that we have the input layer and the output layer, those are always going to be there, as there's always has to be a way to input data and output data. And the output data will, output layer will also be corresponding to the number of outputs you want. So if there's a binary classification, it'd be 0 and 1, so you have 2 outputs. If we had labeling, you're trying to label images, there'd be corresponding final outputs to as many labels as you had. If it was a continuous number from 0 to 1, then, or 0 to whatever, or anything, real number, that would also just be 1. So if we can see, we have inputs, and then we have so-and-so hidden layers, and then final output. We can add as many hidden layers as we can. In fact, a lot of big deep learning models have hundreds of hidden layers. And basically all they do is just allows us to create more complex lines to fit the data within the input space. So this is how it will be represented in TensorFlow. We just have characters.layers.dense for each layer. So N1, N2, N3, N4, so on. How many layers you want and how many neurons you want in them. And then at the end, we have the output layer, which in this case, we want 2 outputs. How can the output represent anything if the output can only be 0 and 1? So the output is not from 0 and 1. It's it can be any number. It's just that moving in between the neurons is what has to be classified between 0 and 1. Do we add a bias to every layer or only from the input layer to the first hidden layer? So we can actually add it anywhere. The point of neural networks is that you can do anything you want. You don't have to have an activation function. You don't have to have a bias. It's just that throughout the years that we've done machine learning, statistical analysis of these models and stuff like that, we just found it best to add biases to each thing so that we're able to better form fit the activation function around the data. Basically, just think of the bias as a way to just move around the activation function so it can best fit the data. Like if you're trying to say y equals mx plus b, if we had a point, if we just had y equals x, but there's a point on 1, 2, we would have to add a y-intercept so that we can move up the line to intersect that point. So let's talk about applying neural networks. So that's awesome. Now we have an idea of not only how to build up a neural network directly from Perceptron, but we also have an idea of how to compose them together so they can form a complex deep neural network. So let's take a look at how we can actually apply them to a very real problem that I'm going through today, and I hope that maybe you guys are going through too. So it's an example problem. Will you pass the class? This is we're gonna simulate a real model, and we're gonna be able to have real input and real output, and we're gonna be able to predict things. So let's start with a simple 2-feature model. Don't forget our features are inputs. So 2 features means we have 2 inputs. So one of them is going to be x1, which represents the number of lectures you attend. x2 represents the hours that you spend on a final project that you have for the class. So we can plot the points on a feature space. So we have data from previous years from utgrades.com. You can see all the people that got grades on there. And we can plot it on this graph. So we have the legend, red, green. Green is passed, red is fail. Actually kind of colorblind, so I can't tell the difference between red, green, and red. So this is kind of a problem. But you should be able to tell. And basically, this is just plotting out all the previous students, and we can see whether they passed or failed based on the number of hours they spent on the final project and the number of lectures they attended. So let's say there's you. So you attended 5 hours, you worked on 5 hours on your final project, and you attended 4 lectures. So that's where to place you, right in the middle. So let's build a neural network to see how we can find out if we're gonna pass or fail the class. So we have to build a neural network with 2 inputs because we have 2 features, x1 and x2, with x1 being the number of lectures that we attended, and x2, the number of hours that you spent on your final project. So we're gonna have 1 hidden layer with 3 units, and we'll feed those into a final probability output by passing the probability output for whether we're going to pass the class or not. And we can see that if we pass in 4 or 5 into this neural network, we will get to 0.1, which is 10%, which is not really good. But if we see that the actual value should be 1, because looking at the other things, we actually passed the class. So that's not great. We got 0.1 when we should have gotten 100% chance to pass the class. And this is the reason why we got a number like that is because we never actually trained the model. Training is very important for neural networks. If we just pass the numbers, it just gives us random numbers out without really doing anything. It just be plugging it into an equation. What's the point? It can't learn. So this model is like a child. It hasn't seen anything, hasn't learned anything. We haven't told the model how to interpret the data. It has to learn everything about the problem first. It doesn't know about whether the number of lectures we attended. It doesn't know that we have the hours that we spent on final product. So it doesn't know anything. So we can't fully accurately predict a probability without teaching it first. So one of the most important things you have to do is you have to actually tell the model when it's making a bad prediction. So it's basically like if you do something wrong, the only way you learn if someone is telling you that it's wrong. And the same thing for a machine learning model, a neural network model. And so this is what loss is. The loss of our network measures the cost incurred from incorrect predictions. So it takes input. The input is the predicted outputs and the ground truth outputs. Ground truth outputs are the ones that are for sure correct, and the predicted outputs are the predicted outputs from the neural network. As we can see, that's given there. That's the formula for loss, or the notation for loss. It's not really a formula. And so if those two things are very far each other, the loss will be very large. That's really bad because we don't want the numbers to be far apart, right? We want the predicted value to match the actual value. On the other hand, if the things are closer to each other, so the loss is near 0, the more accurate the model will be. So one of the things we want to do is minimize loss, also known as optimize it. So let's not just assume that we just have our data point with our experience. We have the data from every student in the class from previous years. So now we not care about how the model did predicting on just us. We care about how it predicts on the whole data set. So this is what we call empirical loss, and it's just the mean or the average of every loss from each individual example or each individual student. Don't forget, loss is just the difference between the two of them for now. So as we can see, the formula is right there. It's a lot of math. JFW is basically just averaging the loss between all the values within our data set. And this is also known as the loss value. It's also known as the objective function, the cost function, and also known as empirical risk if you're in economics. And basically what this does is it helps us quantify how well our model is doing and help it learn whether or not it's making the wrong decisions. So one of the things we want to do is minimize loss so that we're able to get more accurate predictions within our model. So if we take a look at the problem of binary classification, where the neural network in this case has to answer either yes or no, yes being that we pass the class, no being we fail the class, we can use what is called a softmax binary cross entropy loss. So this is defined by the cross entropy between two probability distributions, and it basically just measures how far apart the ground truth probability distribution is from the predicted probability distribution. There's many ways to generate loss. This is one of them. Basically what this is doing is modeling the probability distribution of the whole data set, so it allows us to take into account of everything from the data set. And as we can see, it's right there. This is very common, and it's probably one of the most widely used loss functions for binary classification. Binary classification means there's only two outputs. And this basically just lets us to compare probability distributions between the ground truth and the predicted values. So if we wanted to do something with a regression model, which means it outputs continuous numbers, we'd actually use mean squared error. If you ever took like AP Stats in high school, it's the same thing. So the grade is continuous and not a categorical value such as 0 or 1. We want to use mean squared error, which is basically just the squared difference between our ground truth and our predictions. Again, averaged over the whole data set as we want to take everything into account. So one thing I want you to take away is that depending on the data and depending on the output that you want to give out, there's different ways that you want to calculate loss because of the different ways that it can be. Because if we took mean squared error loss and applied it on a binary classification, output would only be 0 and 1. So it just wouldn't make that much sense to find this mean squared error loss. So we know the loss functions. So how do we minimize these loss functions? This is the most important part of neural networks and it's the most mathy part. So we've seen two loss functions. One of them was for classification binary outputs, and then we also saw one for regression continuous outputs. So we have to optimize them. So how do we do that? How do we train the weights of our neural network so that we can get the correct output? Well, what we want to do is actually find the weights of the neural network that give us the minimum loss for our data set. What this means is that we want to find the weights in our neural network that minimize JFW that we've seen before. And JFW is obviously our empirical cost that averages loss over each data point in the data set. And then we can see here, this is like the math official definition, but what I just want you to take away is that we want to minimize loss. Why is the loss function not just predicted value minus the actual value? So this is a good question. The loss function can actually be whatever you want. It can be whatever you want. You can do loss predicted value plus actual value. It can be predicted value times predicted value. What it's doing is just minimizing that number that you give it. So no matter how or what way you do it, it just wants to minimize that number. So that's the reason why we can't do predicted value minus actual value, because that doesn't help represent our total data set. It just represents that one thing because we're just minusing predicted value minus actual value. But then we just have 50,000 numbers. How do we ask it to optimize all that numbers? We have to ask it, we have to be able to conglomerate it into one number, which is what mean squared error does for us. And there's a lot of different ways that you could do it. It's just that these are the most researched ways and most useful ways that we found over the years and years that we've done this. But it can be any number you want. It can literally just be the number 1, and your machine learning model would also always have a loss of 1 because it wouldn't be able to optimize the number and would never converge on anything. So you just want to try to get that loss number as close to 0, no matter what loss function you use. So it can be anything. It's just that these are the ones that you want to use so that it gives you the most accurate machine learning model if you ever optimize that number to 0. So loss optimization. So remember that our loss is just a function of the network weights. So let's look at this. So as we can see, the y-axis is given as the loss function of 2 weights. And we can see that in the x direction, it's weight 0, and then we can see in the z direction, it's weights 1. If we go back, don't forget that weight 0 is one layer, and then weights 1 is the other layer. This would be a neural network with an input layer, a hidden layer, and an output layer. Weight 0 corresponding to the input to the hidden, weight 0 corresponding to input to hidden, and then weights 1 corresponding to hidden to output. So this basically just lets us visualize like the loss landscape of all of the loss values that we could have inside our machine learning model. So what we want to do is we want to find the optimal W0 and W1 for our machine learning model. So we randomly initialize to a random W0, W1 value. And that can be anywhere on this landscape. And then we compute the gradient, which is this partial derivatives. It's kind of a lot of math, so I'm not going to go into it. But basically what it does is the gradient tell us which way is up. So it's like you're on a mountain. We have to find which way is up. So the gradient tells us which way is up. But we want to go down. So what we do is we take the negative of the gradient so that we go towards the lowest point because we want to minimize loss. We're trying to find the minima of this whole entire plane. So we take a small step in that direction. And then we just keep repeating. We find the gradient. We see that it's up there, so that's ways up. And then we just go down. And then we calculate again, and it's that way. And then we go down. And then we just keep doing that and doing that until we converge upon a point. And what it means by converge is that everywhere around us is up. And what this does is there's a lot of math behind it, but you just have to believe me, but you can look it up yourself, is that this will guarantee that we converge at a local minimum. It won't be the global minimum, but it will be guaranteed to be a local minimum. So what this does is that it effectively lets us find the weights that give us the lowest loss. And that's what gradient descent does. It lets us find the weight that give us the lowest loss, which is the local minima. This is kind of hard to understand, but it's very important to understand because this is how machine learning model training works. You just keep repeating and repeating until you converge upon a local minimum, which is at that point, you can't really train any further, and the loss will be the lowest that can be, and that's obviously going to be the most accurate, as low loss values means that the predicted values are very close to the actual values. So we can summarize this algorithm as follows. This is known as gradient descent because we're descending using gradients. And we initialize the weights randomly. So we can initialize all like that. And then we basically just loop until it converges. So we compute the gradient, which is using partial derivatives of the loss function and the weights. And then we basically just update the weights using the weights minus eta, which is the learning rate, which we'll talk about later. It can be also represented as alpha, and then we with the gradient. So basically what this does is we're subtracting the weights such that the weights that are mu are going towards the local minimum of our loss. And then we return the weights, and then we just keep going and keep going and keep going until we converge upon a local minimum, which means that that's the lowest possible loss that we can get. So how do we do this in TensorFlow? So weights equals tf variable, tf random normal. That basically just generates a list of random weights, which are following a normal distribution. And then while true, with gradient tape as g, this is the gradient field that we saw, the little multicolored thing, like the mouse. And then we can see that the loss is compute loss weights, and then gradient equals g dot gradient loss weights. So what does that mean? That just basically means we're computing the gradient at that point, which means it gives us the highest point. So we give weights minus lowest learning rate times gradient. So we're taking the opposite of that, so we can go in the opposite direction, and then we're reassigning it to weights. And then this loops forever until we converge upon the local minima. I would take a really, really good look at this because this is how training works. And this is how when you if you ever built a TensorFlow model before and you see all the epochs and you see it training, and the output's a loss, this is what it's doing. It's finding the local minima for the loss function and applying the weights. So if we take gradient equals g dot gradient loss dot weights, finding that gradient, I know we just say find that gradient. It's very important to know why we find that gradient. It's known as back propagation, but we don't have the time for that. So if you are on the slides in GitHub, I have some slides about back propagation. I'm going to release some exercises about back propagation and some further reading, but we don't have time to go over it right now. So we're just going to be doing member attendance right now. So if you are a member of AIS, and you probably will know if you are, here's the attendance, here's the QR code, there's a link, and then there's a number. Sign up and fill up. If you're not a member, if you want to be a member, if you're not a member and you want to be a member, our applications open up again next semester. So make sure you apply then. How many different loss functions are there? Infinite. Loss functions can be whatever you want. So known ones, there's about a couple. I mean, the most major ones are binary cross entropy, and for binary classification, and mean squared error for what's it called? Regression tolerance. But you can look up further if you want, or you can even try to design your own loss function to optimize if you are so inclined. How many training examples do you need to get minimum loss? So that just really depends on the data. It's very varied. And one of the biggest things that I learned whenever doing machine learning was just guess and check. You just, forming models, you just want to architect using, like, how do we know how many hidden layers to use? How many neurons do we need, know how to use in each hidden layer? We don't. It's through a lot of intuition. I would say creating deep learning models is actually a creative art rather than a science. And it just really depends on experience and just trying out everything. Try out everything. Everything in TensorFlow is modifiable. You can change anything. You can change how a layer works. You can change how gradient descent works. You can change how the loss function works. You can change how the accuracy works. You can change everything to how you want. I would recommend that you fiddle around with it so that you can figure out how to fully understand it, because the only way you can fully understand it is if you mess with it yourself. So what purpose does the learning rate serve? So why not just do weights minus gradient? So we're going to be talking about this in a bit. I don't know when it comes up, but I'll just give a short answer right now. Learning rate basically just tells us how big of a step that we want to take. So if we have a very high learning rate, we could take a step so big that we actually step over the local minima. And then that means we would just never converge, because if we keep stepping over the local minima, we would just keep like not hitting it. So we would do that. But if we have a learning rate that's too small and our steps are really, really small, that takes so much computation power and so much time to just micro go down this gradient that it would probably take forever to converge. So we have to find the perfect learning rate, which we'll talk about in a second. What is the difference between TensorFlow and Keras? So Keras is a library that was originally by itself and then was taken out by TensorFlow. And basically it just has, it's TensorFlow, but it is easier to create layers through. TensorFlow by itself is very customizable. TensorFlow is used for custom model architecture, and it's used for custom designing your own layers and stuff like that. And you have to do a lot of things manually and construct them yourselves. Keras lets us, by doing this, by putting a whole layer on TensorFlow, that lets us easier access and work with TensorFlow. So anything you do or anything you see online is probably going to be through Keras, or otherwise you have to create it all by yourself, which is just a lot of work. So Keras is what we're going to be working with, and you probably will be working with for most of your life. There's also things such as PyTorch, if you ever want to work with PyTorch. I personally find myself as a PyTorch user. I just find it more enjoyable to work with and easier. So optimization. This is what we were talking about optimizing how we find training neural networks. So training neural networks is difficult. As we can see here, this is just a two-dimensional thing. It's a representation of everything. But imagine if you had multiple dimensions. So instead of a two-dimensional loss graph, you had a three-dimensional loss graph, or a four-dimensional loss graph, or a five-dimensional loss graph, corresponding with the amount of layers that you have. And as you keep getting more and more, it becomes more computationally intensive to calculate these things. So the loss function can be very difficult to optimize. So that's why we have a thing called the learning rate. It helps us optimize it by setting a certain step count for a gradient descent. So as we said before, small learning rate converges very slowly and can get stuck in false local minima, because if you're stuck in a little hole and your learning rate is very small, no matter how around you look, it'll always look like you're in a minima, when there could be a ginormous minima just to the right of you. But since you're in this little ditch, you can't converge to it. If you have too large of a learning rate, you could just step over the local minima. It's very unstable as you're jumping all over the place across the plane, and it will never converge. It'll actually diverge, as you'll never be able to find the local minima unless you somehow happen to just hit that right spot. And then we also have stable learning rates. These are the learning rates we want to use that converge smoothly and avoid local minima, so that we can try to converge to the global minima, which is the best possible loss that we can find for our machine learning model. So how do we deal with this? We can try lots of different learning rates and see what works just right. So for each machine learning model, you have to do 0.01, wait 20 minutes for it to train. Well, it's kind of garbage. 0.02, try it again. It's still kind of garbage. 0.03, 0.04, and this is just brute forcing it. So let's try a smarter way. We design an adaptive learning rate that adapts to the landscape and what we're looking at. So what is that? Learning rates are no longer fixed when you're using adaptive learning rates, and they can be made larger or smaller depending on how large the gradient is, how fast learning is occurring, and size of particular weights, and so on and so forth. You can take so many things into account. And these are algorithms. There's multiple algorithms out there. SGD, Atom, AdaDelta, AdaGrad, RMS Prop. These are all the optimizers within Keras, and there are even more out there that papers are being run on right now. Actually, some people at UTD work on writing optimizers themselves. There's more details if you want to go there. It's a really good article about the history of optimization. One thing that you could do by yourself, and I did this myself a long time ago, and it was very interesting to me and it helped me learn a lot, is writing your own optimizer and seeing how it competes with these optimizers. It's really fun, and you can put it on your resume. You can get a research job somewhere at UTD, because there's a lot of interesting machine learning work that goes on at UTD. But this is all about the math of optimization. So putting it all together, this is a full neural network. if you can see that we have the model defined there, we have 3 dots. So the 3 dots represent the dense layers that we have. And then obviously the input layers would have to be with the amount of inputs that we get. And then we have the n amount of hidden layers with an n amount of size. And I would recommend you guys just to mess around with that to find out what is best for data that you're working with. And then we have a certain amount of output nodes, output layer size, corresponding with the number of outputs that we want. And then we choose our favorite optimizer. In this case, we're doing SGD, which is called stochastic gradient descent. We were going to talk about stochastic gradient descent, but we sadly don't have time. What that does is it basically just lowers gradient descent into batches, and it allows us to beat stochastic noise, and it allows us to parallelize gradient descent so we can faster train it on GPUs and cluster computing. If you don't know what any of that means, don't worry about it. You can just look it up, or you can just use it and just understand that it's really good. And then we can see that prediction equals model X. This is a forward pass because we're just inputting something and getting something out of it. And then with gradient tape as tape, that's the whole loss plane that we have. And then we compute the loss out for that point. And then we update the weights using the gradient to take out gradient loss, model trainable variables. The trainable variables are the weights that can change. And then optimizing about apply gradients. That's basically using our optimizer to help find the best weights as fast as we can to minimize loss. And this is it. This is a whole machine learning model. That's it. This is the basis for many things in the world that you're using today that have been, that people are talking about. This is deep learning. This is it. We've gone through a whole mathematical basis for it. So mini batches, this is called stochastic gradient descent. If you look in the PowerPoint on your GitHub, there's details written about it. We sadly won't be able to go over it today, but it is written there if you want to talk about it. So one major thing we're going to be talking about is called overfitting and so on and so forth. Underfitting too. And underfitting basically means the model doesn't have the capacity to fully learn the data. So this means we're not able to accurately model the data, and we're getting numbers that don't have to do closely with the data at all. We have an ideal fit, which means the line accurately models the data. And then we have overfitting. This is a very complex model that has too many parameters, too many layers, too many neurons, does not generalize well. So that means it will form fit to exactly what you give it. So this is not really generalizable to the outside world. So we can do things to combat this, such as regularization. What is regularization? This is a technique that constrains our optimization problem to discourage complex models to generate these crazy lines that go through every single point within the data. And why do we need it? It allows us to generalize our model on unseen data. So we have the training data, which is things that we're giving our machine and testing out. So this is things we haven't seen. If it becomes overfitted, whenever we give it on unseen data, it will very closely model the seen data it's number for, so it will give us inaccurate results, and it's not generalizable to outside world. Whenever we're building machine learning models, we try to make it as applicable as possible to unseen data so that we're able to generalize the model so that we can be able to predict outputs for circumstances that it's never seen before. So during training, one way to regularize is called dropout. This is called a dropout layer in TensorFlow, we'll see later. And during training, you just set some random activations to 0. So what does that mean? We just cut it out. So one of the most common dropout layers settings is just 50%. So we dropped 50 activations in the layer. So it doesn't make a layer rely on one node. So if we can see here, this is one training example. We have Z13 and Z11 set to 0, it's dropped out. And we have Z22 dropped out. That means it's not going to use that node at all. And this also means you lose 50% of your data in the training process. If we took another training turn, it could become like this, where it turns off Z12 and Z14. So each time it has a random probability to be turned off or on. What this allows us to do is it randomizes, it keeps our model on its toes, and it won't always just focus on the same thing over and over again. It makes it have to learn fully and not just rely on something. But a caveat to this is that you are really just losing 50% of your data. So if you set your dropout layer to 101, that means your neural network just doesn't work at all. No data gets through. And if you set it too low, that means it could focus on the node too much. So this is something you have to test out with and find out to figure out what is the best dropout rate for you. And then we have another way to regularize, which is called early stopping. This is where we stop training before we have a chance to overfit. Because if we see, we go from underfitting to perfectly fit to overfitting. As we train and train more, our model will keep trying to fit and fit and fit until it just draws a really crazy line that goes through all the data points. So let's take a look at this. As we can see, the training iterations, as we go on, the loss is decreasing. We go again, it's still decreased. And then we go again, it decreased. But now, as we keep going, we can see that the testing loss, which is the whenever we run the model on data that hasn't seen before, and training loss, which is running the model on things that it has seen before, is diverging. So what does this mean? That means it's focusing more on the training data and it's not being able to be generalized to the testing data. And then if we keep going, it keeps diverging. So where would be the best place to stop? If we stop training at the 4th iteration, as we can see, that's where it started diverging, but it still has, that's the very beginning where it started to diverge, because we want to be as low as possible with training loss and testing loss. And if we just keep getting, if we have 0 training loss, but our testing loss is 1, that model is completely useless, as that means we can't use the model outside anywhere. And as we can see, before that point is called underfitting, and over that point is called overfitting. So let's do a quick review. We talked about the perceptron, which was the building block of neural networks. It's called a neuron. We talked about nonlinear activation functions. We talked about neural networks and how to build them. We talked about stacking perceptrons to form full neural networks. And we talked about optimization through backpropagation. We didn't, but you should be able to figure out on your own or take a look at it yourself. If you ever heard of 3 Blue 1 Brown, he has an amazing video on backpropagation, and it will explain it better than I probably will ever. And we talked about training and practice. We talked about adaptive learning. We didn't talk about batching, but that's in PowerPoint. I made slides for those if you want to take a look at it. And then we talked about regularization, so we can combat overfitting and underfitting. So what do we do with all this? We actually have a capital contest. We actually have a competition for all of you to participate in. Anyone else want to join? You're going to be given a data set, and you're going to train over that data set, and then you're going to give us your predictions, and then we will score them, and whoever has the highest score at the end of the day wins. There's no real prize. I guess I'll buy you boba if you win through my own funds, but this will be posted tomorrow. We will be having office hours next week by me and anyone who also wants to join. And you can come in and talk to me about troubles you're having with building your competition model and stuff like that. Everything will be released tomorrow, everything will be written out, and then we're going to have a workshop next week announcing the winner and ways to participate in CAD competitions and try to win. We're also going to be going over solutions that you've made, and I hope you guys all participate and join in. It'll be a really good experience to learn about machine learning. And if you ever have trouble, just reach out to me and just keep an eye on the Discord server for when this stuff goes out. And thank you for coming. I'll be posting more stuff on the GitHub, but that's it. And the broadcast.